Hear me?
Yes, sir.
Okay, so I can start now?
Yes, sir.
Okay, so in the previous lecture, what I did basically was the indicial equation way of solving the differential equations, where we will have a singularity in the point y and y. So here there is a singularity of x, the function, and here I have bx divided by x squared is the function. Ax and bx are analytic functions, but because they are divided by x and x squared, they are the singular, so also y. And now there is a technique called the Frobenius technique, by which we can actually solve this. And in the Frobenius technique, what we do basically this is the equation again. Now I use a technique known as a indicial equation technique, which has its basis in complex analysis, and I use y of x equal to x to the power r sigma over m equal to 0 to infinity cm x to the m. The main difference between indicial equation technique and the power series technique is just that in the power series, you instead of starting with you usually start with m equal to 0 and then you sum over cm x to the power m. In the indicial equation technique, you multiply the whole power series by x to the power r, which actually means that you are actually starting from a minimum power of x to the power r and then going on to higher powers of x. Now, r is not determined so far. To determine r, what we do is the following. We expand a of x in a Maclaurin Taylor series expansion as a naught plus a1x plus a2x squared, etc. Similarly, bx equal to b naught plus b1x plus b2x squared, so on and so forth. Then we substitute for y prime, y double prime, and y, as well as a of x and b of x into our differential equation. And what we get in the differential equation is something like x to the power r into r minus b naught plus a naught plus a1x x to the power r c naught, etc. And similarly, we have b naught plus bx, b1x plus b2x squared, etc., times x to the power r, c naught c1x plus c2x to the power r. Now you collect the coefficients of x to the power r and on both sides and equate them. So, or you can collect the coefficients of x to the power r and equate it to 0, because on the right hand side you have only a 0. So if you do that, you get c naught as a common factor, and then we have r minus 1 a plus a naught r plus b naught times c naught is equal to 0. We have chosen c naught as not equal to 0 because if c naught were to be not equal to 0, then the series, instead of beginning with x to the power r, will begin with a different power. So the minimum power of the series is x to the power r, so we can choose a c naught not equal to 0. So if you choose c naught not equal to 0, then r into r minus 1 plus a naught r plus b naught must be 0. So this is actually a quadratic equation in R, and this is called the indicial equation. You can solve this quadratic equation in R and obtain the roots. You can have three different situations. One is the roots R1 and R2 are distinct, and the second one is indicial equation as a double root, which is when the discriminant of the quadratic equation is 0, which is minus, and the roots are going to be 1 minus a naught by 2. The two roots R1 and R2 differ by an integer, that is modulus R1 minus R2 is equal to P. That's another case where P is a positive integer, of course. And in case 1, the two solutions are very simple. You can solve for, as we did in the case of Legendre differential equation, we can solve for the coefficients C1, C2, etc., in terms of C0 or C1, because you always have relation between C0 and C2, C4, so forth, and C1, C3, and so forth. So once you do that, then you will get a differential for U. Sorry. Then you can write down the differential equation as having the two solutions, y1x and 2x. R1 and R2 are different. They don't differ. R1 and R2 don't differ by an integer, because of which y1 and y2 are linearly independent, and you can always write down the general solution as the yx is equal to ay1 plus by2. In case 2, you can write down y1x as before. So we have the initial equation having a double root. And how do you get the second root? It is by the variation of parameters technique, where you assume that y2x is actually ux times y1x, and we want to determine ux. To determine ux, what we do is we write down what is y2 prime x, y2 double prime x, and then substitute the whole thing into the differential equation. When you substitute in the differential equation, the coefficient of u vanishes because y1 is a solution of the differential equation. But so what you get is the x squared u double prime y1 plus 2 u prime y1 prime plus ax times x times y1 u prime. Now we divide the whole equation by x squared y1, and you get u double prime plus 2 y1 prime by y1 ax by x u prime equal to 0. So ax by x can actually be expanded in terms of a0 by x plus a1 by x plus a2 by x, etc., etc. Rather, it is a0 by x plus a1 plus a2 by x, a2 x plus a3 x squared, and so forth. Because a of x you are going to replace by a of x is equal to a0 plus a1x plus a2x squared plus etc., etc. that we have done. The leading term is going to be a0 by x, and we can write down for y1 prime by y1 as a ratio of x to the power r minus 1 times rc0 plus rc1x, etc., etc. And below we have y1, which is xr c0, the xr times c0 plus c1x, etc., etc. This actually I can write it down as just some r by x plus some other terms. So y prime by y is equal to r by x plus some other terms, or I can integrate for y1 prime by or I can integrate for u prime, because if I substitute for y1 prime by y1, this is what I will get. And r is 1 minus a0 by 2, or 2r plus a0 is equal to 1, because of which I have just u double prime plus u prime by x equal to 0, or u double prime by u prime is equal to minus 1 by x plus various other things. And you can integrate this for to get u prime. U prime will be 1 by x times some exponential into something, or integrating again, you have u is equal to ln x plus k1x plus k2x squared, so forth. And the second solution is going to be y2x is equal to ln x plus a power series in x times y1x. So this is generally written in this fashion. Okay, this is how you can get the second solution. A similar way is adopted to get the second solution when the roots of integral equations differ by an integer p. R1 minus R2 is equal to p. So I just told you that. And now I'm going to continue with what is called Bessel's differential equation. So Bessel's equation can be written in the form x minus is equal to. Okay. So new squared can be an integer, or it can be a a fraction or half integer, whatever you want. We will deal with those. So for this, we will use the indicial equation. Sigma T x to the power m plus r, where x to the power power by which you multiply by the power series, and to determine by sigma m r t x to the power y double prime is equal to sigma m plus r into m plus r into x to the power m plus r coefficient cm x to the power m plus r. So what is m m into m cm x plus x multiplied by in the same form m plus r cm x to the power m plus r, and then I have x squared minus mu squared multiplying y, so I will get plus sigma over m is equal to 0 cm x to the power m plus r plus 2 minus mu squared times sigma over m equal to 0 to infinity cm x to the power m plus r. This entire thing is equal to. So if I collect the coefficient for r, then uh, r times t naught. Then this one has x to the power m equal to 0 will only be x plus x to the power r plus 2. So this does not have x to the power r coefficient. Okay, and this term will give me minus nu squared times c naught is equal to 0. So as are you able to hear me?
Yes, sir.
Okay. So m plus minus 0, and because the uh, lowest power of the integral is r, so if we take m into m plus minus equal to 0, or I get minus is equal to 0, or I have m plus r plus nu into m plus R minus nu is equal to 0 because that is what we have. M plus R plus nu into M plus R minus nu is what the solution is going to be. So I will have the solution for R to be M is equal to, okay, since we are dealing with C naught, M is equal to 0. So okay, so M. So what we have is R are the two values. These are the because we have if I do this, so if M R, so so select power X to the power of X. What CM plus uh, M and then uh, 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 this thing CM minus 2 because CM minus 2 is the one X to the power M, then it will be M minus 2 plus CM. So I have CM 2 plus CM minus 2 minus nu square times CM. Okay. M plus R CM CM is actually minus. Okay. This is what we will get 0. So what M nu into M nu minus 1 times CM plus M plus nu CM plus minus nu square times CM is equal to minus of M minus 2. Okay. Or I can say that Cm into okay, so Cm uh, so if I then I will get m p. I have one position m into m plus nu minus 1 plus 1 because r equal to what I have put, and then I have minus nu square is equal to minus Tm minus 2. So I can just a minute, let me move. I can write Tm into m this m plus m plus into m is equal to minus 2 or minus so because what I think is since C naught is related to C2 is related to C4, etc., we can replace m by 2m. So because that is what those I can write C. So this is into m plus okay times 2m minus 3 or I get C is equal to minus C minus 2 divided by into m into m. Okay. Regular 1, 2, etc. Then I'll get C2, C4, and so forth. So I can always put back C2 minus C naught divided by 2 square into m is equal to 1 is 1 output. So nu plus 1 into nu. M is equal to 1. Sorry, this is 1. Okay, so this is for m is equal to 1. So C2m minus 2 will be C naught, and the denominator is going to be 2 square on nu plus 1 into 1, which is nu. And so you should get between very simple. Into 2 square into uh, into 2 is equal to minus C2. So I'll get minus divided by 2 square into 2, and I can actually write it the form minus C plus C naught, because C2 is minus C naught upon 2 squared into nu plus 1. So I'll get 2 to the power 5 into mu plus 2 into nu plus 1. Okay. So this is how I'll get options is the following. So gamma is a gamma. How many gamma functions and beta? Can you hear me? Hello.
Yes, sir.
Have you people done gamma functions?
Sir, no.
Okay, so let me so what I will, this is the part that I'm going to be treating as u prime, and this is a part I'll be treating as v. Okay, so what is equal to 0 minus of uv prime dx. Okay, so this is the part. E to the minus uh, uh, dt is actually minus e to the minus t, right? So what is minus t alpha into 0 to t minus 0 this minus of e to the minus t times t to the power alpha times alpha. Right? So what is the this was plus alpha minus integral e to the minus e to the power alpha, and if then this is equal to alpha times gamma gamma let me see. So when I differentiate, okay. So this is what I get. If I take alpha by the definition of, okay. So because when t to the power, so if it is t to the power of alpha is equal to gamma. Okay. So if alpha, then if I take this is equal to gamma equal to times gamma n minus etc. I go on till gamma 1. Okay. So this is equal to n into n minus 1 to n minus 2 etc. into 2 into 1 into gamma. 1 will be gamma 1. Okay. And what is gamma? Gamma 1 is 0 to e to the minus t, e to the power 0, because it has to be t to the power 1 minus. Okay. So because e to the this is equal to 0 to infinity, e to the minus t to t. And what do I get? I get minus e to the minus t 0 to infinity. This happens to be 1, because when t is equal to infinity, e to the minus t is equal to 0, and when t is equal to 0, e to the minus t is equal to e to the minus t is equal to 1. And since this is at the with a minus, the term is going to give me 1. So what I have, gamma is actually okay. So this can using to alpha, which are fractional, which can be positive or except negative, except for negative. You cannot generalize it to negative integers, but otherwise you can generalize it to alpha values, which are either positive or negative. So these are basically of defining the differential. And gamma functions were introduced by David Bernoulli, and later on, extensively studied by Euler. And gamma and beta functions, that's outside. Into u plus 1. Okay, so that was what we took. So this was, so if C naught So that so times 2. Okay. That was P4. And for C naught, it was okay. So we had this for MX. So that's what I'm upon 2 plus times gamma times times. Okay. Okay. So there was so 2 because the terms of whenever 2m, then uh, then 2m times times gamma. Okay. So this is the expression the power for the coin in the power system for R equal to this for for uh, we can it actually for divided times m times gamma u plus. Okay. So positive or the solution is uh, of the integral is R equal to. So this was a solution that I had for the integral equation because when so we know J and J are linear. mu is not because what happens is I have mu I have. So if not, then x the nu and x the minus nu cannot be expressed or not linearly dependent, and so minus x is not going to be a simple region. Now what happens? Nu is general is a times plus b times a minus uh, uh, then a this is m is infinity minus x to the power divided 2 to the power m plus m factor n plus. So this is what we get. G of m minus x 2m minus 1 x to the power plus n divided by 2 to the power m factorial factorial. Okay, because this is gamma n. So 2 to the 2m times m into m. Okay, now m n so s m minus. Okay, so if I take s is equal to m minus, then the following I can change sum. This becomes sum over s minus n plus. Okay, or 2m because m minus. So okay, because twice m 2m 2m minus that will be so all these are kind of uh, so what s is equal to m minus n, right, and 2s is equal to 2m minus 2n, right? 2s plus n is equal to 2m minus 2n plus n is equal to 2m minus n. So that's what I've got. So this 2 to the power 2m minus n is what? 2 times what is m factorial? M was equal to n n plus into m minus n factorial. Okay, so this minus 1 to n plus 1 second. See, m is minus 1. Okay, x to the power. Sorry. Take it as, minus 1 minus so this one is minus. I can keep equal to 5. See, I have taken minus 1 to the power n outside. I have taken x to the power 2s plus n divided by 2 to the power 2s plus n s factorial into n plus s. So what I have done is basically interchange these two terms, just form as before. So what do you see? You compare this equation okay with or if you want this equation, because I have taken n inside. So this equation with this equation. What do you see? You see that this one is minus 1 to the summation over m. You replace m by s, then you get exactly the same thing as here. And the summation index is always a dummy index, so it does not matter. So this is actually equal to Jn, right? So I have the, the function which is of by various parameters is the following function. Is it obtained I have not. Not called. And the general solution when is y of x is equal to a times jn of x plus b times. Sorry, something happened. See what happened and get back. I'll just stop sharing and reshare again, okay? One second, please. Let me share. Can you see the screen now? Hello?
Sir.
Okay. So I'm sorry, I went off camera. So I general solution y of x. I keep the time. Okay. A jn of x plus b yn of x. So these are the and these are the angles. We are not the power is and sigma over m minus x divided gamma m. Okay. Now let is actually m minus divided by 2 into m plus. So all m now I want this x a prime. Okay. So this sigma over m minus 2m into x 2m plus 2 minus 1 divided by 2 to the power 2m plus m factor m plus this. And now my equal to I'll take out 2 x sigma m is okay, minus x to the power divided 2 to the power 2m plus 8. I have I'll take out okay. So this to give you times I have so I'll get m plus mu because gamma m plus 1 is equal to m plus 5. Okay, or m plus 2 divided by gamma m plus nu plus 1 is equal to m plus nu by m plus nu factorial is equal to 1 upon m plus nu minus 1 factorial because m plus nu cancels the denominator. Okay, so and this is equal to gamma m plus nu. Okay, and x x sigma over minus m divided so yeah okay so this 2m times into m plus so what so if I take uh, a nu minus all you need to substitute for nu equal to okay so then this thing x to the power times x to the power 2 to the power 2m and m factorial okay if you This is nothing but J nu minus 1. Because when it was J nu, you had 2m plus nu here, and you had x to the power nu there, and here you had a m plus nu plus 1. Everything else was the same. So now when you change nu to nu minus 1, this will become x to the power nu minus 1, and this will become 2 to the power 2m, 2 to the power 2m plus nu minus 1, and this will become m plus nu because nu goes to nu minus 1. Okay, so instead of m nu plus 1, it will become m plus nu. Okay. That's what I using select nu plus x j equal to x j j j j this j nu plus 1, and instead of so that's exactly. So I can minus uh, j. So sorry, it's minus x. So once you get it right, this so uh, the okay. So what? So j. Okay. So now what? And multiply by x to the power 2. Okay. If I multiply by x to the power, then what? X j plus x is equal to minus j. Okay. So already I have I just for 2 new, so that I'll get it number 2. Number new plus the next one is j. because a minus x to the power n. Now I okay subtract 2 from. So when you get 2 x to the power ju. So since I'm x to so this and when I subtract here, j nu x sorry, this is equation 1 is f. So nu minus second j is equal to the right hand j nu minus 2 it won't x to the nu into j nu minus 1 minus j nu plus. Since I'm subtracting the beginning, so this is what I okay. So this is the term that I get. Or I can write j plus j is equal to 2 by j of nu. So this is that I'll get by manipulating equation 2. And what happens? So okay. So if I so if what I will get this term plus 2x j nu is equal to j into j nu cut down Okay, so I can minus 2j. So the relationship is very similar to that. Okay, but are infinite. They are not polynomials in the sense that the series does not discontinue after a particular power of x is reached. So they are actually infinite series. So these special functions also have this three-term reconciliation, which is very similar to what we had for orthogonal polynomials, mainly that j nu minus 1 plus j nu plus 1 is 2 nu upon x j nu, that is the three-term recurrence relationship, and the other one is a differential recurrence relationship, which tells you that j nu minus 1 minus j nu plus 1 is 2 j nu prime. For higher order. So you know the special function for say for and plus 1, then the Bessel function. Okay, here what happens? If you want to know the difference of so now do that is very okay. So the operator uh, tells me psi is equal. Okay, so this one for free electron. So in so that you have psi for k is equal to kx x plus k by 5 kz, right? And then minus h plus k squared upon where k squared is the length of the square of the length. But you can also call it so this can also be solved in spherical polar coordinates. And if you do the what you get radially correspond to the R, because when you do the system, so angle theta, you have the angle P, so this if you have R cos theta and x is equal to R cos theta sin P and sorry R with careless. So x is equal to R sin theta, because the project of this project R cos okay, so this and this R, so this is so and y is equal to R sin P. So knowing this variable, so theta 0, because what we have done is basically take if this one, then this is this is theta 0 to pi. Now what you do to rotate this around the z-axis. Like this. So when you then what you we create a sphere by rotating the semicircle around okay. So when you rotate it, the angle phi is going to change. So the phi is going to change between 0 and 2 pi. Okay. So theta will go around the angle phi is 0 to 6. And now if you take the length from 0 to okay, then we span the whole. So if you want to span, then what you have to do is theta has to go from 0 to go from 0 to infinity and phi of 0 to 2 pi. So that is why in the spherical form, integrate 0 to infinity, 0 to 2 pi, and 0 to pi for r theta phi. Now, given r theta equation, okay, so this is the hydrogen atom problem we have done. Separated them into r theta and phi coordinates, and the for the minus del square e to the so some and by 2m. So this 2m mass, yeah, times e to the times psi p, and psi p e to the. Okay, if you have seen the height psi p is the- and the theta part of del square of will give you some the L into n by r square into p l naught cosine theta. Okay, so these are things that are standard. You can look at the answer, then you'll know what is the R part, and the R part of it, if I do the changes of variables, then I have plus plus time 5. Good. To best. This one and what are the solutions of these? The solutions of these are what are called spherical. And the form of Jn of x is the following. Jn of x to the usual phi. So where you had that. So Jn will be actually phi by 2x times J. Okay, and so this in quantum electron gas, then the spherical this free electron you would like the spherical harmonic, the spherical impurity that is free electron gas helps you only to deal with a radial equation, in which case you will encounter the Bessel functions. So this is the form. And these spherical Bessel functions also have what you might call the now suddenly even for which is not we have a Rodrigues formula, and the Rodrigues formula for Jn is the following. Is equal to for n sin x. You remember Legendre polynomials? We just okay. So here I'm going to differentiate it repeatedly by operate repeatedly the operator 1 by x d by dx on this function sin x by x. So what is equal to sin x? Okay, and j1x will sin x by x minus cos x. Okay, so you can always get them. There's also what's called a general. Are of the following form. Cosine minus and then I'm dividing by x. So this t to the power into j n minus. Okay, so the functions. So you may think when you are dealing with quantum mechanics. So that's the reason why I did spherical Bessel functions. But generally, these Bessel functions are one of the most common functions, both in knowing some of the properties of it. So I'm going to stop here today, and we will continue again on Wednesday morning. Okay, and so until then, if you don't have any questions, then we can actually stop it. Okay. So are you guys there?
Yes, sir.
Sir.
Yes.
Yeah.
Okay.
Okay,
Thank you,
so
Sir,
was the
when
audio
we are
better
supposed
today?
to have our final exam?
Yeah, we will discuss that in the first thing next class. The date of the final exam we will discuss first
Okay,
thing
sir.
next class. Okay.